Welcome to Drone Systems and Control course. It's a lecture 8. We're going to talk about basic estimation in this particular lecture. The objective of this particular lecture, by end of this lecture, you should be able to understand the need for the estimation in engineering systems, distinguish between parameter and state estimation, define properties of the estimators, what is required such that you can get the states appropriately, unbiasedness, consistency, what is the efficiency, and you can apply some basic estimation techniques, right, like maximum likelihood or Bayesian estimation, and you understand the principles of state estimation that is needed for the Kalman filter. Okay. See, the previous lecture we talked about sensors. When we mentioned about sensors required for the drone, we had two types of sensors. One which measures the states of the system, something like IMU, which has an accelerometer and gyro. It gives you 3-axis acceleration and 3-axis gyro, and you have a magnetometer which will give you the heading, right? And you have an altimeter. Altimeter could be a different type of altimeter which can measure the height. These are the internal measurements that you could have. And GPS will be there, which will give you the global position information, right? In addition, you have other sensors like camera, LiDAR and radar, which look at the external condition or a context in which the drones are flying. But if you want to control the drone and navigate the drone, you may have to estimate certain states which we discussed in the models of the system, right? Some of the states need to be measured, but we don't have a sensors directly measuring those states, hence controlling them will be very difficult. State estimation is very important aspect which will give us to estimate which is missing information and use that for controllability, right? Controlling the drone and navigating the drone. So this particular lecture is very, very important. Okay. Now, why do we learn estimation, right? Sensors is what we are using. All sensors are not equal to state. That's what I am trying to tell you, right? We have IMU. IMU, if you look at 3-axis acceleration is what we are using. During sensor lecture, I have clearly articulated if you use just IMU alone and if you are using integration to get your velocity and position, they will drift with respect to time. And initial bias will also influence the accurate positions. So we can't just use the sensor accelerometer alone, right? Same with gyro, right? With rate alone you can't get your attitude positions accurately. So that bias and drift is going to be a bigger challenge, right? And then you have a GPS. The biggest problem with GPS is the sensor is very slow, which means you get every 1 hertz data, right? If you are a high speed moving vehicle, let's say 10 meter per second or 15 meter per second, right? By that time you move 15 meters or 30 meters, it's going to affect a lot. Second problem is accuracy of that sensor, right? Triangulation get affected by the environmental conditions where you are flying. If you are driving a vehicle with a GPS for navigation, you know what will happen if it's a cloud. You know what will happen if you go below the tree, right? It will become, one is lag, the other one is accuracy will be affected significantly, right? The jitteriness or slowness will also affect your controllability of the system. Now suppose if you use barometer, right, but it's sensitive to the temperature. So sensors also has its own disadvantage. You need to understand that. So sensors are not just equal to state. So we need to have a mechanism to estimate the state. So estimation bridges the sensing and control. That's another aspect you should appreciate, right? Sensors gets the measurement. Measurement could be noisy, or it could be biased, or it could be jittery, but you need to have an estimator which can help you bridge the gap so that you can have the control properly, right? So you need to understand the reliability aspect of it so that your estimation can work properly, right? Now estimation is equal to understanding the reality, right? Estimator combines the sensor data to infer the true state, right? It's not just using one measurement, you can use multiple measurements to get it, right? You can get your position, You can get your velocity, you can get your attitude information. Sometimes even unobservable states can be estimated. It's very important, it depends on the application perspective. Somebody wants to know what is a wind speed, right? So that I can get to know what is my ground speed, right? Or I can get to know whether to abort my mission or not. You can also estimate some of the unobservable state possible. For that you need to have a specific sensors, which we will discuss later. Okay. Why estimation is important for a multi-rotor system, commonly known as drones, right? We have a raw data, and remember multi-rotors are unstable. It has an oscillatory flight, right? So raw data will have lot of noise, right? And if you want to control the unstable system, you need to get your states measured accurately, right? So you need to have a smooth measurements so that you can use sensor fusion. Either you can fuse IMU and GPS or IMU and camera, optical flow sensor, right? You can fuse them to get your position and velocity information, right? It's very important for you to localize also. If you are talking about autonomy of the drone, it's like moving a drone from one point to another point. So you need to know where you are, right? Where you are is more important so that you can autonomously move from any point to anywhere, right? You will also be able to make a decision by looking at the context information. For example, in later part of the course, we will talk about obstacle avoidance. For obstacle avoidance, you need to know where is the obstacle, what is the shape of the obstacle, what is the relative distance between the obstacle, what is the relative velocity, so that the drone has a compute capability to generate a local path and follow the local path. Once you generate a local path, you need to follow the path accurately, right? So there are factors we need to take into picture. So detection or knowing the obstacle location is also critical for us to do obstacle avoidance, right? So in such cases, you need to know where the obstacle is in global map for us, because if you are saying return to home for some reason and you are coming back, you need to put this obstacle in your map so that when you are coming back, you can generate a trajectory which is safe for the drone to come back to the home, right? So we have to connect various aspects and then decide on what kind of sensors required and what kind of mission the drone is going to perform, and based on that we need to work out on the what states are important and how we are going to achieve that estimation and how we are going to use this information for control and navigation purposes, right? Now another aspect, you want to land precisely. Precisely, let's say you have a charging pad, you want to land on the charging pad, which means precision landing is very important. And you have to do a soft landing if you are carrying an safety critical payloads, right? So we need to look at the objective or the mission of the drone. Based on that, we may have to work out on certain estimations, what is the speed at which you are coming down. It's very important, right, when you are talking about precision landing. Other aspect comes into picture if you are using the drone for inspection inside the building. Your GPS sensor now is not going to be there. So GPS denied information will come into picture. So in such cases, how do I localize? Where am I? How do I navigate to a specific point when I don't even have the GPS information? So navigation in GPS denied environment is also an important factor, right? So now let's look at basic principles or basic understandings. Why study estimation theory, right? We have mentioned earlier with respect to our drone, the measurements are going to be noisy, there is some uncertainty, there is some incomplete information, because if you look at, I want to get the position and velocity, but my IMU is going to give only acceleration, right? The velocity and the position need to be computed. So there is an incomplete information. That's when we start using estimation theory, right? We also want to extract meaningful information from sensor data, right? So I have a measurement, I have another height measurement is available from a sensor. Can I combine this information to get meaningful information for us? What is the meaningful here? I want to know speed at which my drone is moving in 3-dimensional space. What is the position of the drone in 3-dimensional space, right? So we need to get those informations so that we can make more sense out of it, right. And estimation theory is foundational. Where and all its use? Robotics, of course in unmanned aerial vehicle technology, whether even if you go to aircraft, manned aircraft also estimation comes into picture. Wherever we talk about control, all states are not measurable, right. So when you have it, we look at the estimation theory. We also look at it in signal processing. We also use it heavily in artificial intelligence, and wherever we use navigation, estimation theory plays an important role, right. Now let us try to look at estimation in action. Specifics to this particular course, we talk about multi-rotor system. So let us look at our problem, right. We have input. Your input is going to be a PWM signal, and which is going to going through the environment, and you will have a process noise also comes into picture. When I am talking about PWM signals to torque, right, and thrust measurements, right. So you have a different noises could be present. Your electronic speed control system add a noise, and then your motor will also add a noise. Eventually the environment will also add a noise. When there is a crosswind comes into picture, the thrust variations will be there. So I am just looking at those information, and that is going to go into a nonlinear system. The torque and thrust is an input which goes, and you have a measurements. What are we talking of? We are talking of here GPS. I already told you GPS has an error. The error comes due to the cluttered environment and multipath is also possible, and also you have a IMU. IMU picks up vibrations, right. Small vibrations also will be picked up by the accelerometer, and that is also going to act a noise. So that is what I mentioned as a measurement noise, and those information goes to our estimation algorithm, right. That estimation algorithm is sometime I can pass on the input also if it is possible, right. If I am sending the input also, then I am just going to pass all this information to my estimator. The estimator gets me the state information, that is basically a velocity, position, right, and attitude. And once I have it, I can control the drone very efficiently, right. Now what is the goal here? The goal here is to infer unknown quantities, right. That is either the parameter of the system or states of the system using noisy measurements. Remember, estimation theory is basically something learning from data, right. User provides a direct measurements, right, and these measurements are impossible sometimes and it is inaccurate. So we need an estimator which is a function or an algorithm that maps the data to the estimator. For example, I want to estimate a parameter theta, and I have a measurement x1, x2, x3, xn. The theta is a function of x1, x2, x3, xn, right. So I can estimate the position of the drone using IMU and GPS. I can estimate the average height in a population from a data, right. I can estimate the tracking of an object location using computer vision techniques too, right. So estimation plays a role. If you want to track an object in a camera, right, if you are talking about a surveillance solutions, right, you need to know where the objects is in your field of view. You have to continue to track so that you can find out the intentions, right, whether it is going to go straight or is going to go turn right. What is its intention? It is very important in autonomous cars, right. We need to know the other moving object in the scene, what is their intention. Intention can be measured if you know continuously get their two positions, right, and if you continue to track them. Track, when I say, I need to know their position, I need to know the velocity at which they are moving, right. So that is very important, or I need to know even the pose of the vehicle, where it is heading, right. So these are the factors if you want to measure, then again you can use estimation theory, right. Now let us talk more about parameter estimation, okay. Estimating a fixed but unknown quantity, right. Let us say I wanted to find out the time constant of the motor, right. So then I can estimate, that is a fixed quantity, it is unknown, but I want to estimate that. Okay. I can use it for sensor bias. What is a sensor bias or sensor gain to be estimated, right. I can look at the unknown model parameter, what I was mentioning earlier, right, a time constant of the motor. I wanted to find out the mass of the object, right. These are fixed but unknown, I want to find, right. They do not change over the time, these parameters are constant, they are not going to change over the time that I am going to estimate, right. I can apply maximum likelihood method or I can go with Bayesian estimation for these parameter estimation problems. Suppose I am going to estimate the state, moment I say state, they are going to evolve over a time, they are not going to be constant, right. For example, the position of the drone XYZ, velocity of the drone UVW, and I also sometimes want to do actual acceleration, right. If I want to give the acceleration as a command, then I need to know the true acceleration of the vehicle, right. So I need to know the acceleration, they are all going to change with respect to time. Or if I want to control the heading, right, then I need to know the attitude, right, and the rate at which their attitudes are changing. So they are all time varying quantity. Suppose you wanted to decide whether you want to continue with the mission or you want to abort the mission, then you need to know what is the remaining energy available with you. Is that good enough for continuing the mission or not? So which means you have to look at the battery charge level, right. That also evolves with respect to time because you have a fixed charge, right. So these are something which you can use. Here when we talk about state, they are all going to evolve with respect to time. They require recursive update. Whenever the new data comes, you need to find out what is the current position with respect to time. What are the commonly used methods for state estimation? Kalman filter, or you can go with the extended Kalman filter, or you can use particle filter, right. We usually use extended Kalman filter for a nonlinear systems. Okay. Let us talk about an example, right, drone altitude control, right. I want to control the height of the drone. Let us say I wanted to fly the drone at a specific height so that I can inspect the health of the structure, right. So I need to find the current height of the drone. Okay. Estimate the fix, here what is the goal? Fixed property of the system which does not change frequently with respect to time, right. So estimating the motor thrust constant, right. Oh, I am sorry, here we are talking about parameter estimation, right. Thrust constant KT, thrust is proportional to the thrust constant KT and omega square. So I wanted to know how much is the thrust going to be. I wanted to get this parameter so that I can measure it accurately, right. KT is the thrust, T is the thrust which is going to be in kilogram meter per second square. Your omega is a motor speed radians per second, you can measure it. KT is the thrust constant which I wanted to estimate. We can calculate the measurement T and omega during the hover time, right. I can find out what is the vertical acceleration that I could have, right. Thrust that I could get, omega I could get, and I can use this information to estimate my constant KT, right. Parameter estimation here is like estimated parameter which is depends on KT estimate, right, and I can get this information. But this KT might be varying slightly because of my characteristics of the system itself, but they are more or less constant, so I can compute it accurately, right. Whereas if we talk about a state estimation, which means as I mentioned earlier, I wanted to hover at particular time, altitude, right, or I wanted to precise land on a location, right. I need to measure my altitude accurately. Altitude evolves with respect to time, it is going to be dynamically updated. What are the sensors I can use? I can use my IMU. IMU will give me a acceleration when the drone is coming down, right, and also I will get the acceleration in other two axes. I can either use barometer, right, or I can use some altimeters. It could be your radar sensor, which can also measure your altitude, right? But both are noisy. If you are using a single point LiDAR, it also gets affected by the environment. We discuss about what are the different sensors, how they get affected by environments, right. So, the noisy measurements of height is also available. You can estimate altitude in real time. Is the altitude alone is sufficient? We also need to know rate at which you are coming down, right. If you are trying to land, I need to come down at constant rate, right. H dot is also important, or Z dot is also important. Z is my vertical height, Z dot is my velocity, I wanted to know, right. If we talk about soft landing, what does it mean? The velocity at which you are coming down should decrease with respect to time. When you touch the surface, velocity should be equal to 0, closer to the surface. Now, the other constraint will come, can height be negative? What does it mean? You are impact the ground already, right. So, height cannot be negative. When height comes closer to some epsilon, I will cut off the motor so that the drone touch the ground with minimum impact, right. So, you need to estimate these two if you want to do precision control of altitude. So, measurement here, your barometer reading or your radar or LiDAR reading, which will give you what is your current height, which is noisy, and you have accelerometers available, and you can use your accelerometers from your IMU. You can estimate your Z and Z dot. I am just trying to give you an example here. By doing an estimation, I can show the true altitude and estimated altitude, how close they are. So, you can ask your question, how do you get the true altitude? Let us say I do it in a motion capture system, for there is an external sensor which can just detect my true altitude. So, I can just find out how good is my estimator here, right. Just to continue on this, how do we do the fusion here, right. I can get the altitude, vertical velocity, these are required for us, so that we can control the whole system. Barometer is giving, let us assume I am going to fix the sensor here, is going to be barometer, which is giving me altitude Z. I know it is noisy. I have accelerometer, which gives me the thrust and Z double dot, right. Basically acceleration in vertical space, right. You have a motor speed or thrust command, which is also available. Basically, you are trying to say what is my input. Remember, we did the parameter estimation, I know the KT and I know the omega. So, I can get some estimate of my thrust, which is available, right. Now, I can use Z dot is nothing but my vertical velocity, and V Z dot is equal to KT omega square by M. M is the mass of the drone minus G. So, I can estimate my true altimeter ZKM, it is my measurement, is true ZK plus noise. Your true acceleration measurement AZM is equal to V Z dot, it is a true acceleration, and you will have a sensor bias plus noise, right. So, I can use extended Kalman filter for fusion. What I want to get? My states Z and Z dot, right. Z dot is nothing but my velocity, right. What are the inputs that is available? UK, which is omega k, omega is known. When I say k is a sampling time at time k, right. UK is the input, which is nothing but omega. What are my measurements? Y is the output, which is Z plus some noise, V is a noise, Y2 is that is a position measurement with noise, Y2 is your velocity with some noise, right. So, I have those measurements, I can try to fuse them, right. Now, I also talk about another application, right. I can identify unknown uncertain physical property of the drone. We will talk about Kalman filter, how to formulate the Kalman filter, how do we estimate these measurements in more detail in the next lecture. I am just trying to give the motivation where we will use, how we will use, how the measurement is, right. Suppose there is a goal, I want to identify uncertain physical property of the drone, Okay, I want to find my yawing moment Jz, right. The yaw rotational dynamics, if you look at, it depends on moment Jz, y psi double dot equal to tau z is your torque, right. Psi is your yaw angle, tau z is your yaw torque. So if you use known torque input tau z, measuring the yaw acceleration, right, rotational acceleration psi double dot, we can estimate Jz, right. What is the moment of inertia about the z axis, right. So we can estimate this parameter too, right. Suppose you are trying to do heading control. You want to use what is your psi dot, what is the yaw angle or yaw rate in which the drone is rotating, right. I can use a gyroscope, gyro measurements, right, which will give me rate, right, psi dot, and I can use a magnetometer to get my heading, right. We know these sensors are all noisy and has a drift, right. I can use an estimator or a extended Kalman filter. I can fuse this information and compute psi and psi dot. Okay. Just gave you an example here how the true value will be, how the compass measurements of and how do I get the true estimate how closely they are matching with each other. Just to give understanding, when I talked about noisy, you will get an idea. You can see that compass informations are fluctuating. So that shows how noisy the data is. You can see in the bottom graph when we talk about yaw rate, right, our gyro measures rate, how noisy it is. That will show in some insight into it, right. What are the estimation properties if you look at? I need to be unbiasedness, I have to be consistent, I have to be efficient, I have to be robust. When I talk about what is unbiased, a estimator should be unbiased if expected value equals to the true parameter, right. On an average it hits the true value. What is consistency? Estimator should be consistent if it converges to true value as the sample size increases. So theta n is an estimate, converge to theta as n tends to infinity. More data, better estimate. Efficient. Estimator is efficient if it has a low variance among all unbiased estimator, that is measured relative to Kramerov lower bound. Okay. Robustness, estimator is resistant to outlier, violation of assumptions, model deviations, right. Example, median is more robust than mean. Now bias of the estimator, right. Bias is one of the most important characteristics of an estimator. It measures systematic errors in the estimator. It also tells us if the estimator on an average get the right answer. A bias of 0 means it is unbiased, right. Bias measures how far the expected value of an estimator is from true parameter. So expectation of theta hat minus theta is my bias, right. Unbiased estimator, what will happen? Expectation of theta hat will be equal to theta, which means the bias is equal to 0, right. Imagine if you are using ultrasound sensor to measure an altitude above the ground, right. Let us say the true altitude is 2 meter. Okay. Sensor has a systematic calibration error due to temperature or mounting angle. It consistently underestimate the altitude by 0.2 meter, right. So it is like I kept my drone at one particular position, I fixed, it is not flying, it is not moving, let us say. I know the true value. Due to the temperature variation, due to the way it has been mounted, right, there is a consistent error of 0.2 meters, which means the bias is 0.2, right. Lower bias means it is very close to the true value. Okay. So you need to understand between the bias and variance, right. I can be my variance may be small, right, but I can have high bias, right. I have a low bias, but my variance could be high. So you need to understand how the measurements are, right. The other one is covariance of the estimator. The variance of the estimator measures the spread of its estimate around the expected value, right. What we are talking of, expectation of theta hat minus expectation of theta hat whole square, right. So variance we are talking about. If an estimator is unbiased, it might produce very scattered results for different samples, right. Variance captures the stability of the estimator. Even if estimator is correct on an average, it produces widely different values on each run, it is not useful, right. So, think about it now, I am just at height 1.8, every time it says it is 1.7, 1.4, right. If the variance is there, it is a high variance, it is not really useful, right. Low variance estimates are reliable, close to converge, right. High variance means they are inconsistent, right. So you have to get the bias value, you also have to understand the variance, and that will help us to decide what to do, right. For a larger n, variance of the estimator decreases. If you do more measurements, variance will decrease, right. Sometimes estimators reduce variance at the cost of bias, right. This leads to a concept of mean square error, right. So we look at the bias and variance and try to see how good our estimate is. Just given you a figure here for you to understand between a low variance and high variance, right. In the context of the drone, what is that covariance really means? If the drone is flying straight, let us say to the north, and GPS noise is symmetric, right, then the XY error are independent. So covariance of XY is closer to 0. If the wind pushes the drone northeast, the GPS estimate both XY together, the error in XY increases together, right. So which means the covariance of XY will increases with respect to 0. If GPS overestimates X while underestimate Y or vice versa, what will happen? Error move in opposite directions. So covariance will be less than 0. So you have to understand what is happening inside, right. Now let us get a bit more detailed understanding of how mean square error is going to play a role. MSE quantifies the square difference between the estimator and the true value. It also tells us on an average how far our estimator is from true value, right. But what makes it more powerful when you combine two things, bias and variance, right. It captures both accuracy and consistency of the estimate, right. Accuracy talks about how closer you are, the consistency is how reliable your measurement is, right. Ultimately what we want something with a low bias and low variance. You have 4 choices, right. You can have low bias, high variance, or low bias, low variance, high bias, low variance, or high bias, high variance. You have 4 choice comes into picture. Suppose let us say you have 4 different estimator, right. Well, let us compare 2 of them. One estimator has low bias, but it has a high variance. There is another estimator which has a high bias, but very low variance. What is better? Estimator B is better, okay, because the variance is small, right, and therefore it is preferred even though there is a bias, right. But ultimate aim is to get low bias and low variance. I do not want even the bias to be there. High variance is dangerous, right. Every time you measure it says you are at a different height, then you may have to, your controller will start reacting and you start consuming more energy, keep correcting it, and your mission time will come down significantly, right. Okay. Sometimes a biased estimator can outperform unbiased one, right. In autonomous drone you might prefer consistent estimator even if slightly wrong, right. That is a message. It results in more predictable, reliable performance overall, right, and will also help us to plan better, okay. So now let us get a little bit more understanding on bias. Imagine you are using a ultrasonic sensor, right, in your drone to measure your altitude above the ground. Let us say your altitude is 2 meters, right. Unbiased estimator, the sensor is very well calibrated, right. It gives you accurate measurement, right. The measurement comes out to be 2, right. That is on an average, it equals to the true value, hence it is unbiased. There is an estimator 2, which is a biased estimator, means the sensor has a systematic calibration error. It could be due to mounting. You are planning to mount the ultrasonic sensors, but it is tilted for some reason. Because of that, there is an error, right, and the error is 0.2. Then overall measurement, if you look at, expect your measurement will be 1.8 meters, right, which means the bias is 0.2. Even if the estimator has a low variance, the systematic shift makes it biased. It does not capture the true value on an average. Okay. Now let us look at the variance aspect of it. Let us try to understand this. Okay. Same, I am using ultrasonic sensor, same scenario, I have mounted it. The true altitude is 2 meters. I am measuring it continuously, right. Sensor 1, estimator 1 has a low variance, right. What does it mean? Every time it computes, it is closer to the true value. For example, whenever I get estimate is 1.98, 2.2, 2.01, 1.99 and 2, right. You can see the variance is low. It is centered towards the true value theta, it is a great estimator, right. If I talk about high variance, let us say I am using an average as an estimator, right. Then what happens, sometime it gives me 1.8, 2.2, 2.05, 1.95 and 2.0, which means the variance is high. Even if it is unbiased, it is less reliable, right. Even both estimators are unbiased, one has a low variance, is more trustworthy, right. Many critical systems, we do not want high variance, right. High variance cause instability or unpredictable behavior. So we want to have, even if you have a bias is fine, but my variance should be low, that is very important, right. So let us get more understanding. When I am looking at both bias and variance together, I am trying to explain it in a sense. Let us say I have one estimator who has a mean closer, right. My variance is, let us say, 0.2 square, which is 0.04, bias is 0, my mean square error, if you look at it, is 0.04. I have another estimator, but low variance, let us say the mean is 1.9, right. The bias is going to be, variance is going to be 1.9 minus 2, that is 0.1, the whole square is 0.01. Variance square, if you look at it, it is going to be 0.01. If you look at mean square error, right, it is 0.01 plus 0.01 is 0.02. Even though the estimator B, right, or estimator 2 is biased, its overall mean square error is lower due to smaller variance, right. So even if it is unbiased but has a high variance, it is not suitable. That is a message I wanted to bring it in. Even the estimator is biased, it has a low variance, it is preferred, right. So we look for estimator which gives you a low variance, right. It is very critical. Low variance, low bias is preferable, right. In a summary, this particular lecture gives you an overview of estimator, why estimators are needed, how it is useful to get the parameters of the system, how one can use the estimator to get the continuously evolving state which is not measured. We gave a different examples of it with respect to multi-rotor system, which is drones, right. We can estimate the time motor time constant or thrust constant or even moment of inertia, right, or we can use it to estimate states of the system like position, velocity, attitudes with different sensor fusions, right. More importantly, we looked at different properties of the estimator. we try to look at what is a bias, what is a variance, how do we choose the estimator which has a low variance, effect of variance, and their influence in the control part of it, right. In the next lecture, we will discuss more about how do we design the Kalman filter to estimate the states which is evolving continuously, because it is very important for us to estimate the states, and these states will be used to control this drone in subsequent lecture, right. So, we will focus on Kalman filter in the next lecture, followed by some examples, how do we implement them, how do we compute in MATLAB. Thank you.